fired up.
Hey, Jonathan, light your shirt on fire. Hey. Yeah. Are you ready?
Okay.
I am ready. Yes.
So,
I have to go. I will see you.
you post the video.
Okay. Have a good weekend. Happy Easter.
You too. See you.
Good luck.
Okay. So let's chit chat about the lab. So hopefully by now you have a graph where you have graphed absorbance on the y-axis and concentration on the x-axis, which hopefully is pretty linear. Now, that's why I said I looked at your data and that first stock solution, that absorbance for some of you didn't like fit the trend. So don't be afraid to like just throw that one out because it's just it would give you exactly. The other ones all kind of fit that pattern. So just don't worry about that. So here's what's important is the slope of this line. Now, in the instructions, Isaac Bruce, you listen to me. In the instructions, I tell you, circle the points on the graph that you're going to use to find the slope. Boom. Couple of points. Write those points down. Okay? Because everybody's slopes are going to be different. Okay? Everybody's points are going to be different. It's the only thing I can grade you on is the process. This is what some of you are fighting me on. Well, I got the answer. I don't care. If your work doesn't generate that answer, I was like, well, I did it on my calculator. I don't care. Okay? You are trying to convey information to me that says, hey, I understand how chemistry is done. At this level, you are not in a freshman science class where all they care about is the answer. I am concerned more about the process, especially on labs, than I am about the answer. Make the work create that answer. Show me the calculation of that slope. So, hopefully, and if you look at the units, the absorbance doesn't have any units. So then you have your concentration, which is in micromolarity. So the cool thing about this is that your slope doesn't have any units, okay, in terms of your y value, but it does in terms of your x. So hopefully your slope is around something around, and this is a huge-ish, something around 0.07, okay? Should be some variation on that. Like if you have a slope of 15, that's bad, okay? But it should be somewhere in that neighborhood, okay? But like I said, there's some variations based upon that. Now, the whole point of this lab in terms of how this is going to play out today, you have what's known as Beer's equation. And no, don't sit there and go, Beer. Doesn't have anything to do with it. So what you're trying to figure out, and over here on page 2 of the lab, on that backside, I tell you exactly what everything is. So what this is, here's your absorbance, okay? That's what you're going to get from the machine. How much of the light is being absorbed by the crystal violet solution, okay? So you're going to have that number. What's not going to change is A and B, okay? A is called your molar absorptivity, and that's just a function of whatever the solution is. So crystal violet has a certain value. We don't know what the number is. We don't care what the number is, okay? B is the path length. That's how far, basically the distance across the cuvette. Again, that's the same every time. So we don't care what these numbers are. They're just going to be a number. And these two numbers multiplied together are going to be some constant. So basically what we're saying is that A is going to equal some constant times C, all right? So here's the whole point of this story, is that once you realize that this is a linear function, then if you go back to this as being y equals mx, okay? So if you know what the absorptivity is, or excuse me, what the absorbance is, then if you know what the slope of the line is, then you can figure out what the missing concentration is. Yes.
So is the units of slope the inverse nanomolarity?
Yeah, they get weird. Yeah, no, the slope itself is just it's just 1 over micromolarity. That's just what the slope of the line is. Now, so here's what's going to happen today. Now that you have, this is why you have to have the slope of this line. Because once you have the slope of the line, then you can generate the equation that says, oh, okay, if I know either one of these, either the absorbance or the concentration, I can figure out the other one because then it's just a slope integral. It's just y equals mx plus b. So today, here's what you're going to do. You're going to take some crystal violet, and you're going to react that with some sodium hydroxide. Now, the cool part about this, there's a couple of things about this that are cool. One is that the reaction takes place pretty slowly. Okay? It isn't like we mix them together, bam, the reaction is done. This takes a while. So what you're going to do is you're going to mix these together. And what's going to happen is that over the period of time, the concentration of your CV ions is going to go down because this has a distinctive purple color to it, and the CVOH is clear. So on an atomic level, what happens is that you change the structure of the chihuahuas. The CV plus, as light goes through it, basically absorbs the light, but it reflects off the purple light. That's why you see it as purple. So the only way you can see something as purple is if it's either emitting purple light, which this isn't, or it's bouncing the purple light off of it, and you see that as purple. So if something's clear, like water, any number of solutions, those are clear because of the fact that as the photons go through there, nothing happens. Okay? The chihuahuas just go, hey, stop. Okay? And the chihuahuas just let him pass through. So basically, you're going from altering the structure of the chihuahuas, where they bounce off purple light, to the fact that it's going to go clear, and then they're going to let him pass right through. So as time goes by, the concentration of your CV plus ions is going to go down. So what's going to happen then, in terms of the graph, if you know what the absorbance is, then you can figure out what the concentration is. So on that data table, squirrels, spinning platforms.
You want mine?
Yeah. Thank you. Okay. So here's what you're going to do. You're going to quickly as possible mix up the CV plus and the sodium hydroxide. Put those together. As soon as that happens, then you're going to take some of that and pour that into a cuvette. You're going to put that cuvette into the calorimeter, close the lid. As soon as you close the lid, start the clock. So what's going to happen is that every 30 seconds, you are going to measure the absorbance, okay? And you're going to do that for a total of 300 seconds, all right? So you go dink, 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 and you're going to measure that absorbance. Now, from that, knowing the absorbance, then you're going to go to your graph, or the mathematical function of that graph, and knowing what the absorbance is, then from that, you're going to determine the unknown concentration. Okay? That's what's going to go here. So you've got to calculate what the concentration of the crystal violet is based upon the time, your absorbance, boom, you're going to have that. Once you get this column, then, because we don't know what the order of the reaction is, then you're going to take the natural log of your CV, the inverse of that, and we're going to try and figure out, hey, is this a first order or is this a second order reaction based upon the graph. So the second graph that you're going to draw is one where you're going to have time, natural log, CV. Y'all have done this before. That should be old hat. Now, sometimes these graphs look pretty similar. And so I hate to bias you with this, but if you don't end up with this, then all the other questions that you're going to have are going to be a train wreck. So what should happen is that this should be a first order reaction. Okay? So hopefully the natural log versus time one is more linear. Sometimes on this graph, it's kind of hard. It's like, ooh, which one's more linear? Assume that's going to be first order. Hate to bias you, but otherwise, if I don't bias you, some people might think, oh, it's the second order. It's like, no, it's not. It's the first order. Mr. Jones.
So the y equals mx thing is like what we're using to find the concentration for this part?
Yes.
Okay, and so it's a equals kc. Are we using like the slope that we found and anywhere in that equation?
Yes. That's what that, so the slope represents,
N?
yes. So that's what you should have is the slope of that line.
So it's the absorbance equals the slope that we found times the concentration of CV?
Yes.
Okay.
So, well, no, you're going to have the absorbance. The absorbance is what you're going to have. So you're going to take your absorbance and divide it by the slope of the line to get your concentration. Okay? Now, here's the other important thing that's going to happen. And we're going to do what's known as a pseudo rate law. Okay? So on a pseudo rate law, even though when you look at this reaction, it should be dependent upon both the concentration of your Cv plus ions and the concentration of your hydroxide ion. But what we're going to do is we're going to make the concentration of the hydroxide ions so much bigger than the concentration of the Cv plus ions that functionally the concentration of your hydroxide ions doesn't change enough to make any difference. So it'd be like going to the ocean and taking out a cup of water. Okay? Did you change the volume of the ocean? Technically, yes. Is it going to make any difference? No. So on a pseudo rate law, what it does is that it allows us to focus on just what's going to happen with the Cv plus. So basically, we're going to overload this thing with hydroxide ions so that functionally the hydroxide ion concentration remains the same. Then we can say, okay, now we're only going to be dependent upon the Cv plus. It's like we don't want to change both. Then, like if it changes, we don't know, hey, is this changing because of the hydroxide? Is it changing because of the Cv ion? We don't know what's going on. So if you maintain the concentration of the hydroxide ions big enough, you don't have to worry about that. Now, from a colorimeter standpoint, why did we don't want to use hydroxide ions in the colorimeter? Why? They're clear. It's like, okay, we changed the concentration of the hydroxide ion. Great. It can show up on a pH scale, but it's just not going to show up on colorimeter. So that's why we're going to change the concentration of the Cv plus ions. I want to maintain the concentration of the hydroxide ions be so big that it functionally doesn't make any difference. So that's going to be important when you get to these questions over here on that procedure part. When it's going to say what percentage of the hydroxide ions that remain at the end of the reaction, okay, if it goes through, and then on the hydroxide ions. So that's kind of keep that in mind. What's going to happen is that we're going to maintain a high concentration of the hydroxide ions, but we're going to let that go back. So on question number 6 on that back page, it says review the conditions. It says which mode ratio described should be used to ensure that the Cv plus ions can be treated as a pseudo rate law. Basically, the one where you have a huge difference between the concentrations so that one of them remains constant and the other one changes. When you get to number 11 on that back side, it says draw a best fit line and determine the slope of the graph, circle the points on the graph, and write down the corresponding x and y values. Again, everybody's data is going to be different. The only thing I can base this on is your graph, is your slope. So like I said, hopefully, and about 90% of the time it does clearly work out that you recognize it as a first order. But just in case, assume that it's going to be first order. Now, when you get to questions 14 and 15 on that back side, says when looking at the absorbance concentration graph, what is the possible explanation for a point that is well below the other points? So in other words, you did this. You drew this graph, you had absorbance, and you had concentration, okay? And instead of being this nice linear function where everything is on the same point, you got a graph that looks something like this. So you had this, you had this, you had this, and then it says on 14, you have a point that's well below the other points. And then you have one point that's down here, but you have the other ones up here. So here's the question. What could have happened to create that low point? Now, here's the answer that you do not give me. Oh, it was human error. Okay, bad. Oh, the calorimeter read it wrong. Bad. Okay, neither one of those answers are acceptable. So what you want to think about is that, okay, you're measuring absorbance versus concentration. So what we're saying is at this particular data point, something happened that absorbance went way down, okay, well below the other ones. The other ones were fine. What could have happened to create that? Now, keep in mind you were doing a series of dilutions, okay? So what could have gone wrong in that process? Did you add too much water? Did you add too much of the crystal violet?
It's not human error.
But human error,
Specify.
I'm just saying you can't say human error.
Yeah, you have to specify.
Now you specify what that human error is, I'm cool with it. But just to say, oh, it's human error, okay? No. Like physically something had to happen. Now, on 14 or 15 is the opposite, okay? Instead of having a point that's well below, you have a point that's way up there. What could have happened to make everything else linear and that point was well up above? Think about physically what had to happen in this process. Oh, here's this cuvette, and you're shining that light through. So either too much light got through, more than what it should have, or not enough light got through. What could have happened either way to make that happen? Okay. Other than that, I think we're good. So this lab is going to be due on Tuesday. The test is going to be on Thursday.
Well, isn't he just a bunch
Okay. Yeah. Hoppy the bunny rabbit just folded into the room. So